and that is a pleasure for us. JBP has been in Malaysia since 2008, and the idea of our company was to bring knowledge, know-how, and technology, mainly from Europe, into Malaysia. As Frank mentioned, we have been in the industry for many years, and there's always two sides of the coin. To be for good, but also maybe you get a bit too square minded if you don't get new influence. But as my policy has always been, with help I can do everything by myself, and that is how I have survived over the years. Here in Malaysia, we have been, as I mentioned, for quite some time, and we have, beside that, been working in many countries around the world. Actually started back in Japan in the early 90s with little experience, but year by year that has also grown. I'm Swedish by birth, live in Spain, have a main office in Germany and half of the family in the UK. Now we never know what's happened with the Brexit and so on, but that is another side of the story. So we are actually getting information also to teach as much as our participants at the courses. Important is to exchange experience. In different countries you have different conditions and need different kind of adoption of the technology to be used. So I'm pleased to have so many experts around here. If you look at the region where we have been active, it started back in Singapore, went over to Malaysia, and also we have done work in Vietnam and Indonesia. The group, it's a small group which consists of 4 companies. So we started back in 2004, and in 2008 we established a first company in Malaysia, followed by consultancy service and a contracting company back in 2013. If you look at the sewer network in this country, we have about 20,000 kilometers. 20,000 kilometers. We have roughly about 20% in a critical state. So that is something you have much bigger knowledge than we have, and therefore I will just highlight this one. I would like to hand over this to my colleagues, but before I go further, I would like to give IWCAN a big thank you for all the support you have done for us to be able to be here. Frank, for all the work you have done together with people here to organize this course. As I said, with help, I can do everything by myself. Last but not least, my old good friend, Dr. Deb Doney, which will kick off this course. Dec is a legend in this industry. He has many years of experience. I will not tell how many, because I don't know if I tell this kind of big figures. But he is a legend in our industry, and we are very pleased and happy to have Dec here to support ourselves and, of course, yourself. Like Frank said, the course here will be a wide, broad course in trenchless technology, but I have to say that we have one of the biggest experts here today and tomorrow. So, with that, I would like to say thank you so much for showing up this morning, and I'm really looking forward to these 2 days to come. And I leave over the stage to Dec.
Excuse us a moment.
Once again, good morning. It's very nice to stand here in front of you. I don't plan on standing much of the day, but I am going to be up here much of the day, so you might see me sort of slipping back on the desk and relaxing, because people of my age usually take a nap about 10 o'clock. We have 3 sessions today, sort of session on current methods and technologies. Later this morning, this afternoon, we'll talk about the benefits and limitations of trenchless technologies. And finally then talk about a little bit about selection and a lot more about the design of lining systems. And at the end of that, I've got a spreadsheet that I'll put on the screen to show you an easy way of doing the design work. And you could decide what parameters you'd like to put in. Change them around. It's just a matter of sticking the data in, and it'll come up with a line of fitness. You get a feel for how easy it is to operate and what simple process it really is. So I'd like to begin really by first of all working out how to use this. This isn't working. There'll be a reason why it isn't working.
Forward back.
Is it turned on?
Sorry.
Right. So that's my basic lesson. We pointed out for it.
Should just that computer. No, it doesn't have to.
Doesn't matter at all.
Sorry.
I think I'll leave.
I must have the magic touch. Just one quick touch.
I think I'll be too far.
Try again. Sorry.
I think it's the cactus plant.
Try that. You see if it goes.
Okay. Great start to the day. I want to talk a bit about sewer construction, which sort of started a long, long time ago and gradually shifted into Europe. So it's just a bit of interesting background. Give you a feeling of where pipeline construction has come from and how it's worked. So we'll have a quick look at how historic materials have been developed, where they were developed, how the networks grew. We'll then talk about the standards that operated at the time that these pipes were first installed. A little bit about the problems which everybody knows about, that if you don't fix your pipes, if you don't maintain your pipes, they're not going to function, and you're going to have problems quite soon. In fact, serious problems. And then we can look at how assessments have been made and how that's driven expenditure in various countries. Take us into the 1980s and the beginnings of the trenchless technology era. As we've been at it now for 30 odd years, I think we can reliably call it an era. It's not just a question of time. So it did work. So in the up until about the 19th century, we've had we've got In the 19th century, we had major cities of Europe, North America, and indeed India. And they had culverts which took stormwater to rivers, and the water was taken care of in that way. We had solid waste being separated and carted off and used as an agricultural fertilizer. And that was a viable business when cities were relatively small. But as cities grew bigger and bigger, it became impossible in a day to truck solid waste out into the countryside and use it reliably. And so cities were in danger of being overwhelmed by their own sewage. And I'll tell you a little anecdote about how Tokyo was totally overwhelmed by the sewage when we get to that point in the presentation. We have mainly very traditional materials. Bricks have been made since about 4000 BC. We've had clay pipe being made since 2000 years ago, of various kinds. And then we got into a well-documented problem in London, where the Prime Minister was Disraeli closed Parliament down because people were choking on the smell coming off the Thames. So a lovely place to be. Holidays in London in the 1850s were not that popular. So we have clay pipes and clay brick from, as I say, 4,000 years ago. We have masonry brick sewers constructed in Rome and in any other city that the Roman conquesting armies took over. So London had sewers in about 100 AD because the Roman army got there, built a little city. They built it where the Thames was narrow enough to throw a bridge over the Thames, and the river was big enough for ships to come up from the North Sea into what became the capital. In those days it was just a Roman place, not a significant place at all. But it became significant because it had clean water and dirty water processing really quite early in its history. And then not a lot happened for quite a long time until the 18th century. There were stoneware pipe sewers put in a lot of cities around the Mediterranean. Paris in the 16th century put in stone sewers lined with stone, with cut stones. And some of them are still functioning today. We have the massive sewer which runs into the Tiber in Rome, and that's been functioning as part of the public system for over 2,000 years. It still is. But we didn't see any major change in things until the invention of a machine to manufacture clay pipe in about the 1830s. The clay pipe were limited in size up to about probably 150, 200 millimeters in diameter. They were very short, little joints every couple of feet in length. And as you know very well, wherever you have a pipe joint, you're probably going to have a leak. So that had some way to go. And then we had the invention of cement, or cement as we know it today. This was invented in 1827. It wasn't particularly good, it wasn't particularly reliable, but before that you had what was so-called Roman cements, whereas they were pozzolanic cements, made from naturally occurring materials, which came from a Mediterranean town called Pozzolana, pozzolanic cement. In the 1827s, they learned how to blend the right minerals and fire them and then grind them back to make cement as we know it today. It hasn't changed enormously since that time. But one of the great things was that in the major era of sewer construction in the 1850s and 60s, somebody began to do quality control. That meant that they could weed out the very poorly fired cements from the equipment. And a major step forward there. So in the 1850s, we began to see cement pipes being made, and in this great stink era, when a major £4 million was spent to construct about 95 miles of major interceptor sewer, 1,000 miles of feeder sewer. And £4 million then was probably about £300 million today, so quite a big expense, mostly, and invested all in about 10 years to construct this network. After that, people began to get more confident of putting steel into cement products, so they made steel reinforced pipe. The earliest pipes were probably in the 1850s. There's a pipe being dug out of a trench in New Jersey, which is supposed to have been made in 1847. Nobody really knows. Like many things in that kind of antiquity, the legend is probably better than the truth of it. And we had pipes being made from cast iron, then spun iron pipes, and then ductile iron pipes in the early 20th century. Asbestos cement was made in the 1930s, which doesn't seem to be such a good idea today, does it? And we had plastic pipes invented in the 1950s and 60s. PVC and GRP pipes, all of which have problems, all of which continue to have problems, and you have to deal with some of those problems now. Probably AC is a big problem, I guess. So that's a little bit of that background. Pipe there on the top left-hand side, that is the Clerco-Maxwell Road, which is still functioning. It's a stone-lined culvert, man entry size, runs right under the city of Rome, delivers sewage into the River Tiber. On the bottom there is an early clay pipe from about the early 18th century. And on the right-hand side of the picture, you've got a number of clay sewers. All of these shapes were built into the sewer system in Manchester. Now, what we see there is actually what we see in which might well be satisfactory for that length of time necessary to do. If we look at continuous slip lining, this is not an exaggeration, this is a real job where someone inserts a, I don't know, I guess about 450, maybe 500 millimeter polyethylene pipe into what, 750 millimeter steel pipe. So there's a huge loss of cross-section there. But also the challenge is you've got to get that polyethylene pipe centered properly, otherwise your invert level is going to be fluctuating. So to do this job properly, you're probably going to put timber bearers underneath the pipe and slide the plastic pipe in place on top of them and then grout all around it. But of course what many contractors don't do is they don't grout. So you're left with a pipe that floats and can be problematic. Because once debris, detritus gets underneath this pipe, if it's not done properly, then there's forever going to be a lump in the alignment level, which is going to be a problem for operational capacity in the pipeline. But you can imagine that the loss of cross-section area is absolutely huge there, and that's the general disadvantage of that kind of process. So I'd say we'd use slip lining generally in pipes of a metre plus. Obviously there are smaller pipes with a slip line from time to time, because it might be the cheapest option, but it might be a perfectly satisfactory option. They tend to be used for large pipes, because large pipes have very often got excess capacity. Our Victorian ancestors were very good at making large pipes with plenty of spare capacity, and that's proved to be a great virtue of historic pipes. Whereas today our engineers tend to be much more precise in flow studies and in actually tailoring the pipeline they're making to the predicted flow. So we're much more sensitive then to getting it wrong. So a large circular or egg-shaped pipe with more complex shapes, probably in sizes up to 3 metres. And I say 3 metres because 3 metres is probably the size of pipe that you would happily carry on the back of a truck, longitudinally along the bed, with the necessary timber work to protect the pipe. Because your truck is bouncing along the highway, you don't want your plastic pipe to be deflecting due to the loads put on it from the the lorry bed bouncing up and down. So we have to move our pipes very carefully during the initial stage before they're in place and properly grouted. So if we're going to be lining large pipes, then we're going to be putting in some kind of flow control, or perhaps working at night when the flows are generally lesser. We need simple equipment. You need a crane to move the pipe. You need something to push or pull the pipe in place. Or perhaps, in the case of discrete lengths of pipe, particularly those complex shapes, we'll take a 4 or 5 meter pipe length into place on a carrier, a frame on wheels or something like that. As you travel around the world and look at these kinds of work, you can see some very interesting engineering by the contractor who's thought up a practical way of putting the pipe in place. You can line pipes quite quickly. If you can line a large diameter pipe at 15 to 20 meters an hour by slip lining, compare that to 15 to 20 meters a day if you were replacing the large diameter pipe. It's a very attractive option. But you have to do the grouting properly to provide a pipe that's going to work for a length of 50 years or whatever in the future. And then you've got the issue, often with large pipes, the big problem of where do you put the pipes during construction. The clever contractor will bring 3 or 4 pipes to the work site, and then bring more pipes during the course of the day, so that he can keep it in step with his installation rate. The lazy contractor will bring in 200 metres of pipe and leave them strewn along the road and cause no end of trouble to the community and so on. So it's quite difficult. If you're going to be doing more complex slip lining, the kind of thing where you're reducing the pipe in cross-section, then you've got other issues of the footprint on the work site that we'll have a look at in a moment. We also might think that you can just shove a pipe into the existing pipe. You know, anyone can do it, and it tends to be done by general contractors rather than specialists. But actually, you need to do the job properly, and that involves a CCTV survey beforehand and afterwards to check that the pipe is properly installed. But in particular, to do it beforehand and the day before or the night before, so that you can be sure that there are no obstructions to stop you pushing or pulling your new pipe in place. In some places where I've worked on slip lining projects, you have a little local difficulty because they've done the survey a month before the installation work, and in the meantime someone's got a couple of dead cows and a few bicycles in the inverted pipe, which then get trapped underneath the lining, which is not a good thing to do. You might, with continuous slip lining, have long lengths of pipe that you want to pull in place. And these might be welded together on the work site. So you've got to have space set out to do that. If you think about trying to do that in a side street, you've then got to think about bringing your long length of welded pipeline round the corner into the pipe. And if you think about pulling that pipe 5 meters down to the invert, you probably need a 40 or 50 meter long trench to get it to the invert level without overstressing the pipe when you're doing it. So it's not as simple as it might seem. And if you overstress a plastic pipe during installation, which is easy to do, then you're going to shorten the life of that pipe quite considerably, particularly in a pipeline that involves pressure. So we might see polyethylene pipes in sizes up to 1.5 meters, GRP pipes up to 3 meters, and we might, with continuous slip lining, might get some really fast installation speeds. But to work at that speed, you've really got to plan the work properly and carefully. Otherwise, you're just going to get a mess, which involves months and months of rework. This is a tunnel lined in the Malaysian YTL Corporation using their operation at Wessex Water. This was done last winter. It's a 1.8 metre tunnel. It was a particularly interesting project, and it's been written up in a couple of the magazines and journals if you'd like to read about it. The engineer, Julian Britton, who did this project, is critical sewers manager for Wessex, And I've said to a number of people that you should take advantage of the fact that YTL own this company and talk to them, because it's all kind of part of the family. And Julian himself used to work in KL on microtunneling projects, so he's very keen to come back and talk to you if he had the opportunity. What he did here, he had this existing pipeline with pretty large cracks in there, and he wanted to know what was behind the pipe. And so he took a bit of lateral thinking. And if you go to hospital and have a bit of a check on your hiatus hernia, they shove a camera down your neck. Or if you have other problems, they may put a camera in a different direction. He got a camera which he inserted up through the cracks, so he could go back and measure the size of the cavity above it and make a proper estimate of what he needed to do in pre-work before lining to secure the hose pipe before lining it. So he also used a system developed by the City of Paris and an engineering firm. And this is a method, I can't really describe it accurately, but I'll describe it practically. You have a couple of load sensing devices on a crosspiece, and you put that on a frame inside the pipe. You jack the crosspiece out so that you apply the load cells onto the two extremities at the spring line level of the pipe. So you can measure the amount of deflection and the load required to deflect the hose pipe. So it's a method of measuring the in situ stiffness of the hose pipe. So you can make an assessment of how much stiffness that pipe could contribute then to a renovated pipeline. It's a clever technique, it's been well documented, but it was the first time it had been used in the UK. And that's what YTL and Julian Britton do. They do a lot of things for the first time, so they're good people to talk to. I did the design on the pipe. This is the endoscope that they used, inserting it up into the cracks in the pipe. And this is the City of Paris system for monitoring the deflections and the pressure required to create those deflections. A very sophisticated method of working. The pipes were designed using the German ATV method, which is another option that we'll talk about very briefly this afternoon. And these are other examples of, you see here the contractor is putting in pipes to graft the lining in situ. This is a circular pipe being put in a shaped invert of a more complex pipeline. And in some sections, and that's the finished product being checked before acceptance. I mentioned early this morning the sewers of Calcutta. These were constructed in the 1850s. They were relined in 2012, 13, and they are big pipes. This is big money. And this is one of the things, if I were wearing a hat, I'd be taking my hat off to the engineers in Calcutta, because they used great ingenuity and great courage to adopt lining systems without there being a recognised contractor to do the work, and without them having any experience of doing the work. You could say they were foolhardy, they weren't. So they've now got not just these three lines, but lots more lines like that. They've lined something like 50 kilometres in the last 10 years. Large diameter sewer, thus restoring the pipe. So this pipe is probably going to have a 250-year life, because it's 150 years through already. And the finished job is really good to look at. When these pipes were excavated, they were so heavily silted that they'd lost 85% of the cross-sectional area to silt, bicycles and other debris that tends to find its way into Indian sewers. It was very often done by man-entry excavation, teams of people with shovels, small excavators and so on. Well, they weren't that small, that was in the biggest one. But quite a challenging project. And if you're interested to look at this further, go into Google, or go into your internet search engine, and put the name Sue Perkins into the search engine. And Sue Perkins in Calcutta Sewers. Sue Perkins is a comedian who does a lot of programs about interesting things around the world. She went into this sewer with the chief engineer of Calcutta, Mr. Basu. Mr. Basu is himself a character. Sue Perkins is quite a character. And when the two of them get 5 meters down into the invert of this sewer, with a veritable river of sewage pouring past them, they had a very interesting conversation. It's a sort of 3-minute video. It's well worth looking at. She admonished him for not looking very confident as he climbed down the ladder into this sewer. But you should have seen her when she climbed down. She was hanging on for dear life. And I've been down there, and I can see why. It's not great. But that's a wonderful job. That's the new pipe going in place. And these guys had never done this before. There was a small Austrian contractor brought in to show them how to do it. But he hired local people, local subcontractors to do the cleaning. And over a 3 to 5 year time span, they have done a colossal amount of work, very, very successfully. Curing place lining, the granddaddy of them all, developed in 1971 in a 900mm by 600mm brick egg-shaped sewer in the old part of London, in Brick Lane in Hackney. I went down this sewer in 1991 to help take some samples of the material that had been in situ for 20 years by then. And I went back in 2001 to take some samples when it had been in situ for 30 years. We took the samples off to the standard testing laboratory and had strength measurements and flexural modulus measurements made on the lining. And actually, considering that was amongst the first, probably the first 6, 7, 8, 9, 10 linings ever installed, the linings installed were actually really very, very good indeed. And over 20 and 30 years in service, they were still considerably stronger and less flexible than you would expect modern material for sewer lining to be, of that felt and resin nature. It was done in a very crude way. The fabric was impregnated with resin, and the liner was pulled in. The ends were drawn together and tied up with a cord to make it like a sausage, perhaps, and a small inch diameter hose was inserted into the end of the sausage, and an air pump connected to it and was gradually brought up to size and pressed against the size of the pipe, left for a week to cure naturally, and when they came back and cut the ends off, it was put back in service. And it's a good thing to go and look at. I'm hoping that we're going to go back and do samples at 50 years in service, which will be 2 years' time. But I'm thinking I'll let somebody else go down there this time, because I don't bend as well as I used to. But it's very exciting to have the opportunity to visit something quite as historic. I visited it in 1991 with the chief engineer from the city of Yokohama. And unfortunately, halfway along the length, he got a panic attack, and he had 2 colleagues behind him. And this was, as I said, a 900 by 600. Now, I know many Japanese people are not very big, but he managed to climb over 2 of them on the way out. I don't know how they did it. But we all got into the receiving manhole, and we said, "Where's Mr. Obayashi," or whatever his name happened to be? Oh no.